Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Maxwell-Boltzmann law of distribution of velocities in an ideal gas. Let's begin. In the previous video lecture, we discussed about Maxwell's Boltzmann distribution law. So, here from Maxwell-Boltzmann's distribution law, we can derive Maxwell-Boltzmann law of distribution of velocities of an ideal gas. What is that Maxwell-Boltzmann distribution law? From Maxwell-Boltzmann distribution law or distribution law of energy. Ni is equal to Gi divided by e to the power alpha e to the power beta into ui. Here Ni we take the intervals or components like 1, 2, 3 up to k number of intervals or components. Here we take ith interval. Here we take ith interval where the number of gas molecules in that of ith interval be Ni and the energy of that ith compartment will be ui, and it is divided into further elementary cells, that is Gi, which is known as, means that ith compartment. If I take that is the ith compartment, this is the ith compartment, ith interval, that is divided into Gi number of elementary cells, that Gi, which is known as the elementary phase cell. And we get that particular equation, Ni is equal to Gi divided by e to the power alpha e to the power beta ui. That Gi is known as the phase space cell. Gi is the phase space cell of ith interval. What is phase space cell? Phase space cell, we take this unit cell here, that phase space cell, to determine the position and momentum of that of particle inside that of phase space cell. We take three position coordinates and 3 momentum coordinates are needed to describe its position and momentum. Combining these two, we say that is 6 number of coordinates are required to describe the phase space cell, and the volume of that of phase space cell, the volume of the phase space cell is written as H naught Q. This is all about phase space cell. Okay. So to derive that equation, we take the energies or in discrete manner in the sense, here the energy be U1, here the energy be U2, here the energy will be U3, like that of for ith compartment the energy will be Ui. But to derive or evaluate the value of constants as alpha and beta, we consider the energies are not discrete, but it will be continuous. So, to derive the constants alpha and beta, we take the energies are not discrete, but these are continuous. These are continuous. Rather than discrete, we take the energies are continuous. So, let the number of molecules in that of interval, let we calculate, let the number of molecules, the number of gas molecules, we take the ideal gas here, the number of molecules in that of unit energy interval, in that of unit energy interval around U. If I take one of the interval, so the unit energy interval of U will be U minus half to U plus half, that is the energy range U, that is the energy interval around U in the sense, around U in the sense, that is the energy interval, in the energy interval that is U minus half and U plus half is the energy interval that is around U. That is the what should be the number of molecules, number of molecules in that of energy interval around U in the sense, that is U minus half to U plus half, that is the range. What should be the number of molecules? It is denoted as, that is NU, that is denoted by NU, means the number of molecules in that of energy range U minus half to U plus half, and that is given by, therefore Nu, that is the number of molecules in that of unit energy range, will be how much? Nu is equal to Gu into Gu into e to the power minus alpha, e to the power minus alpha into e to the power minus beta U. Take equation number 1, where Gu, that is the number of phase space cell, number of phase space cell, as we say here, phase space cell, number of phase space cell in that of energy interval, in that of energy interval. Energy interval means U minus half to U plus half, that is energy around that of U. Let me take the mass of the molecule. Nu is the number of molecules, how many molecules are in that of energy region. So, if we take, let the mass of a molecule, let mass of a molecule be small m, and velocity of the molecule, velocity of molecule BV, then the momentum of that molecule, therefore momentum of the molecule, that is P, is equal to mass into velocity. Again the kinetic energy of the molecule, again the kinetic energy, therefore the kinetic energy of molecule, kinetic energy of the molecule, that is the, in case of that ideal gas, the total energy is only due to that of kinetic energy, and that kinetic energy is given by, kinetic energy of that molecule is given by, that is U is equal to half mv square, or U is equal to, that is m square v square divided by 2m. There will be no such change. I just multiply m here and divide m here in that of numerator and in that of denominator. So U is equal to mv square divided by 2m. In place of mv we substitute, that is the momentum, that is p square divided by 2m. Now putting the value of U in that of respective equation, equation 1. So equation 1 becomes, equation 1 becomes, that is Np, Np is equal to G of P e to the power minus alpha into e to the power minus beta p square divided by 2m. What exactly that equation indicates? Where we say Np, where Np, that is the number of molecules, that is the number of molecules in the momentum range, in the unit momentum, unit momentum interval, that is p minus half and p plus half Np. Again Gp is the number of cells, G of P, that is the number of cells in that of unit interval, p minus half and p plus half, with the mean momentum p, number of cells in that of unit momentum interval p minus half and p plus half, that equation indicates. So if the number of molecules in the momentum interval dp, that is between p to p plus dp, so what should be the number of molecules, the number of molecules in the momentum interval dp. dp means that is between p and p plus dp, that is between p and p plus dp. is given by, that is NPdP. NPdP. NPdP means the number of molecules in the interval dp. dp means between the momentum p and p plus dp. That is g of p e to the power minus alpha e to the power minus beta p square divided by 2m dp. That is equation number 3. Again here GPdP is what? Here GPdP, that is the number of phase space cells in that of momentum interval dp or p to p plus dp. That is the number of phase space cell in the given momentum interval. Momentum interval in the sense, that is momentum interval dp means p to p plus dp. NPdP is the number of molecules in the momentum interval dp, and GPdP, that is the number of phase space cell in the momentum interval dp. Now in that of phase space cell, the phase space cell we consider the volume of that of phase space cell. Let me define let the volume of a phase space cell be H naught Q. Then according to our definition, GPdP, what is GPdP? GPdP is the number of phase space cells in that of momentum interval dp. So GPdP we can say that is the volume in phase space cell in that of momentum interval, that is the volume in phase space in momentum interval p to p plus dp divided by volume of a phase space cell. Volume of a phase space cell. Here the volume of phase space cell in momentum interval p to dp. We know the in phase space cell we take 3 position coordinates and 3 momentum coordinates. So here the volume will be 6 time integration, 3 for position and 3 for momentum, that is position coordinate dx, dy, dz, and for momentum that will be d px, d py, d pz divided by for unit phase space volume, that is H naught Q, as you define, is equal to separating the position and momentum coordinates, that is the integration of position dx, dy, dz, and again the integration of momentum coordinates, that is dpx, dpy, dpz divided by H naught Q. That integral is the volume, triple integration dpx, dpy, dpz divided by H naught Q, where V is equal to dx, dy, dz, that is the volume of gas in position space. Here we take only position coordinates. that is the value of what? GP dP, number of phase space cells in that of given momentum interval. Now you have to determine the value of that integral term. How we have to determine that integral term? Let us determine the value of, let us determine the value of what? That integral, momentum integral, dpx, dpy and dpz. How we have to calculate these three? To calculate that one, we have to take, assume three mutually perpendicular axes. Three mutually perpendicular axes here you take three mutually perpendicular axes. As we say, let that is px, py and pz are three mutually perpendicular axes, and these three are intersecting at origin O, and draw the sphere of radius p. We take the sphere, as we take the three dimension, so we take the sphere, that sphere having the radius of that of sphere be p, with the radius of that of sphere, with origin O as that of center, and then all points on that of sphere will correspond to that of momentum p. Here the momentum p, here the momentum p, here the momentum p also. Now we draw another concentric sphere. Concentric means the center will be same, and that concentric sphere with the radius p plus dp. So the sphere look like this. This is the concentric sphere. That distance will be dp. Then the volume of that of element, volume of these elements is nothing, that is the triple integration of dpx, dpy and dpz, volume within this. So the volume of molecules with the momentum, therefore we calculate volume of the molecules with momentum between p and p plus dp, means the volume within this is equal to volume of that sphere minus volume of this sphere. So volume of sphere with radius p plus dp minus volume of that inner sphere, that is volume of sphere with radius p. Therefore the volume of molecules with that of momentum range, that is triple integration dpx, dpy, dpz is equal to volume of that of sphere, that is 4 pi by 3 cube of that of radius, that is p plus dp whole cube minus volume of that sphere 4 pi by 3 p cube, 4 pi by 3 taking as common, so p plus dp whole cube minus pq, that is 4 pi by 3. So a plus b whole q, that is aq plus bq plus 3 ab whole into a plus b minus pq. Here pq cancel out. Inside that of bracket term, that is 4 pi by 3 p square dp plus 3p dp square plus dpq. Since we take dp is small, therefore its squares are and cubes are very small, so we neglect dp square and dp cube. Since dp is small, so dp square and dp cube are very small, then we neglect these terms. The only term exists, that is 4 pi by 3 3p square dp. 1 3 cancel out, that is 4p square dp is 4 pi p square dp. That is the value of this integral. Triple integration of dpx, dpy and dpz. Let we have to put this in that equation. Therefore gp dp, therefore the value of gp dp is equal to v into that much gp dp, that is 4 pi h naught q, that is p square v dp, that is the value of gp dp. Now look at that of equation number 3. Equation number 3, np dp is equal to gp dp into that quantity. So putting the value of gp dp in that of equation 3, we have equation 3 becomes np dp, that is number of molecules in that of momentum range, is equal to 4 pi p square divided by h naught q v e to the power minus alpha e to the power minus beta p square divided by 2m dp. That is equation number 4 here. Now we have to evaluate the constants as alpha and beta. That is the number of molecules in that of momentum range np dp. So what should be the total number of molecules in that of momentum range? Then we have to integrate that one. So to calculate the number of molecules, therefore the number of molecules, the total number of molecules of the gas is given by, just to integrate that term. So total number of molecules with the n, that is the integration from 0 to infinity np dp. Putting the values here, np, that is 0 to infinity, the value of np put it here, that is 4 pi p square divided by h naught q v e to the power minus alpha e to the power minus beta p square divided by 2m dp is equal to the constant term to that of outside 4 pi v divided by h naught q e to the power minus alpha, then integration over 0 to infinity p square into e to the power minus beta p square divided by 2m dp. That integral can be solved using the standard integration. So here we use the standard integration. From standard integration, take from standard equation, standard integration, standard integral, we have integration from 0 to infinity x square e to the power minus a alpha square dx will be how much? That is 1 by 4 pi divided by a q square root. This is the standard integration. Here we use the standard integral to solve that particular integration. The value of that of integration will be how much? That is 4 by 3, that is 4 pi by h naught q v e to the power minus alpha, that value will be 1 by 4 pi divided by beta by 2m q whole root over. So simplifying that term, we have n is equal to, that is the total number of molecules, v e to the power minus alpha divided by h naught q 2 pi m divided by beta to the power 3 by 2. This is the total number of molecules. From this total number of molecules, we can consider e to the power minus alpha. Our aim is to calculate the constants alpha. So e to the power minus alpha will be, therefore e to the power minus alpha will be how much? N h naught q divided by v beta divided by 2 pi m to the power 3 by 2. This is the value of beta e to the power minus alpha. Now the equation, as you say, equation number 3, npdp is equal to gpdp e to the power minus alpha e to the power beta p square 2m dp, and that equation changed to another equation as we take the value of gpdp. Now we find out the value of e to the power minus alpha. So e to the power minus alpha is put here, then equation changed to, so equation number 4 becomes, equation number 4 becomes npdp is equal to 4 pi p square divided by h naught q v n h naught q divided by v beta 2 pi m to the power 3 by 2 e to the power minus beta p square divided by 2m dp, or NPdP, that is 4 pi n beta divided by 2 pi m to the power 3 by 2 p square e to the power minus beta p square divided by 2m dp. Simplifying that one. Here we know that u is equal to, here we know that u is equal to p square by 2m, u is equal to p square by 2m, which implies p square is equal to 2m u. Now differentiating it, we have 2p dp is equal to 2m du, or dp is equal to, which implies dp is equal to m by p du, which implies dp is equal to m, in place of p we substitute that is under root of 2mu, that is under root of 2mu du, or dp is equal to, that is 1m in that of under root cancel out, so it will be m divided by 2u under root du, that is the value of dp du. Now the value of dp is substituted here. So what we have, that momentum change to in that of energy range. So we have or nu du is equal to 4 pi n beta by 2 pi m to the power 3 by 2 2mu into e to the power minus beta 2mu by 2m into the value of dp, that is m by 2u m du. Now it can be solved, that is nu du is equal to 2n by root pi, that is 2n divided by root pi beta to the power 3 by 2 u, that is u to the power, here half minus 1 by 3, here 1, so it will be u to the power 3 by 2 e to the power minus beta u du. That is the equation nu du is equal to that much. What exactly that equation indicates? That is the number of gas molecules in that of energy range u to u plus du. That equation gives, this gives the number of molecules having energies between u to u plus du. In that of energy range, this is the number of gas molecules. So the total energy of that of system consisting n molecules will be what? To integrate that one. Therefore, the total energy is given by, that is U is equal to integration from 0 to infinity U nu du, that equation 0 to infinity, that is 2n by root phi beta to the power 3 by 2 u to the power 3 by 2 e to the power minus beta u du. Look at that equation here, that is u to the power half, u to the power 1 to minus half, that is u to the power half, not 3 by 2, that is u to the power half. But here u is multiplied to that of u to the power half, it will be u to the power 3 by 2. Okay. So, that is 2n by root pi beta to the power 3i as constant to outside, that is 0 to infinity u to the power 3 by 2 e to the power minus beta u du. This is one kind of standard integral. So, from standard integration, the integration from 0 to infinity x to the power 3 by 2 to e to the power minus alpha x dx, that type of integral result will be 3 divided by 4a square under root of pi by a, that standard integral is used here to solve this integration. So, here we have the result like that of 2n by root pi beta to the power 3 by 2 into here 3 divided by 4 beta square under root of pi by beta. Under cancellation we have u is equal to 3n divided by 2 beta, that is the total energy possessed by n number of molecules. So, from the definition of equipartition energy, the kinetic energy per molecule of the gas at temperature T will be 3 by 2 kT. Here the total energy of system of n molecules, that is u is equal to how much? 3 by 2 n kT, that from equipartition energy, the average kinetic energy per molecule, that is the average kinetic energy per molecule is equal to half kT for n number of molecules, sorry, that is 3 by 2 kT, that is 3 by 2 kT, K be the Boltzmann constant, T be the temperature. For n number of molecules, so that will be 3 by 2 n kT. Here we get u is equal to 3n by 2 beta, that is 3n by 2 beta is equal to 3 by 2 n kT, or 1 by beta will be 1 by 3 by 2 cancel out, n cancel out, 1 by beta is equal to kT, or beta is equal to 1 by kt. That is the constant value, beta is equal to 1 by kt. Therefore, the equation as we derived in case of equation number 4, what we have? Look at that equation number 4. 4 equation can be changed to equation number 5 as we put the value of e to the power alpha here, then that equation changed to here the equation number npdp okay. When we take the equation as npdp, that value will be this much. Now we substitute the value of beta in that of equation. So that equation, when we put e to the power minus alpha and the value of beta, so that equation changed to, so we write therefore npdp means the number of molecules in that of momentum range p to p plus dp. We just put the value of e to the power minus alpha and beta as we derived the two constants. That equation will be 4 pi n 1 by 2 pi m k t to the power 3 by 2 p square e to the power minus p square divided by e to the power minus p square divided by 2m kt dp. Again simplifying this, that is np dp is equal to root 2 pi n divided by pi m kt to the power 3 by 2 p square e to the power minus p square divided by e to the power 2m kt, sorry, that is e to the power 2m kt dp. That is the required expression npdp. What gives that equation? From that of equation, that equation gives npdp is the number of molecules, that equation gives the number of molecules of gas having the momentum between p and p plus dp, and this is known as Maxwell-Boltzmann's distribution law of momenta. That is known as Maxwell-Boltzmann distribution law of momenta. How many number of particles or number of gas molecules in that of momentum range. Again, now putting the constant beta is equal to 1 by kt for that of energy expression. Here the energy expression we taking into consideration, here we take the energy expression nu du is a 2 pi root pi beta to the power 3 by 2 u to the power half e to the power minus beta u du. So here we put the value of beta as 1 by kt, so that equation changes to, therefore nu du is equal to 2n by root pi 1 by kt to the power 3 by 2 u to the power half e to the power minus u by kt du, or simplifying that one we write it as nu du is equal to 2 pi n divided by pi kt to the power 3 by 2 u to the power half e to the power minus u by kt du. What exactly that equation gives? That is the number of molecules in that of energy range. So that equation gives here, that equation gives the number of molecules having energy between u and u plus du of an ideal gas, at temperature T, and this is known as Maxwell-Boltzmann's distribution law of energies. Maxwell-Boltzmann distribution law of energies. Number of particles in that of energy range u plus du. But we know that next we calculate number of molecules in that of velocity range. So we know that P is equal to mv, differentiating dp is equal to mdv, so let me take that equation as here v is the velocity, and take the equation number as equation number 5, that one let equation number 6. So equation 5 becomes, that is nv dv is equal to 4 pi n 1 by 2 pi m kt to the power 3 by 2 m square v square e to the power minus m square v square divided by 2 m kt into m dv. Just simplifying it, we write nv dv is equal to 4 pi n m divided by 2 pi kt to the power 3 by 2 v square e to the power minus m v square divided by 2 kt into dv. That is the number of molecules, gas molecules in that of velocity range. So that equation gives, this equation gives the number of molecules having velocities between V and V plus dV of an ideal gas at absolute temperature T, and this is known as Maxwell-Boltzmann Maxwell-Boltzmann's law of distribution of velocity. Law of Boltzmann's law of distribution of molecular speeds or velocities It is Maxwell-Boltzmann's law of distribution of velocities. This is Maxwell-Boltzmann distribution law of velocities. This is the Maxwell-Boltzmann distribution law of energies. This is Maxwell-Boltzmann distribution of momenta. NPdP, number of particles in that of momentum range. NUdU, number of particles or number of molecules in that of energy range. That is NVdB, the number of molecules in that of velocity range. So, with the help of this video lecture, we understand what is Maxwell-Boltzmann law of distribution of velocities in an ideal gas, that can be derived from that of Maxwell-Boltzmann distribution law. We proceed like this. First, we have to find out the value of constants like alpha and beta. To derive that one, we proceed in this manner. The total number of molecules, this is one of the constant e to the power minus alpha is derived. Then putting these values, again total energies, and comparing that total energies. Okay, to derive GPdP, what is the value of GPdP, can be established in this way. GPdP, the value of GPdP is derived. Now put it the value of e to the power alpha and GPdP. Here we get e to the power alpha term and GPdP values are put it. Finally we get NUdU, the final energies, the total energies. To use the total energy according to the concept of equipartition, law of equipartition of energy. So we get NPdP, that is the number of molecules in that of momentum range, and this is known as Maxwell-Boltzmann distribution of momenta. And again the value of beta is put in that of energy expression. So NUdU is equal to that much, that gives the number of gas molecules in that of energy range, which is known as Maxwell-Boltzmann distribution law of energy. And again taking P is equal to mV and dP is equal to mdV, that equation changes to that one, that is NVdV, which is the number of gas molecules in that of velocity range, and that is known as Maxwell-Boltzmann law of distribution of velocities. So with this useful and informative notes, let me wind up this session. Thank you.